All right, I have some bad news for you, and the bad news is that your standard errors are probably wrong, and you need to fix them. So standard errors and fixing them is a scourge of the applied econometrician or anybody doing causal inference, and it's something that you will have to face as you are working in this field. So what do I mean? Well, what is it? First of all, we've been talking about the standard error of our ordinary least squares coefficients, right? That is the standard deviation of the sampling distribution of our coefficients. And we need those standard errors because that tells us about basically how much we actually know about our estimate. How precise of a claim can I make about what this coefficient is or is not? Well, I've also given you this calculation here in order to calculate those standard errors. But the problem is this is not like the definition of the standard deviation of ordinary least squares. It is a calculation that is based on some assumptions. If those assumptions are wrong, then this calculation will no longer actually reflect the standard deviation of the sampling distribution, which is bad because that is the only thing that we calculated it to be able to do. So what are some of the assumptions that we have been making, and what happens if those assumptions are wrong? Now, to reassure you a little bit, if these assumptions are wrong, the main thing that's going to happen is that our estimate of the standard error is going to be wrong and we'll need to fix it. Our ordinary least squares coefficient will usually be fine. That's good. But we still do have to make sure that we get our standard errors right, too. So what are those assumptions? Well, one of them is we can get out the way really quickly. One of the assumptions that we're making is that the error term in the model, our epsilon, if we do y, is regressed on beta 0 plus beta 1 times x plus epsilon. We are assuming that epsilon is normally distributed, that it follows a normal distribution. Now, this is a misunderstood assumption, by the way. Many people take it to mean that we have to make sure that our variables, our x's and our y's, are normally distributed. We don't. We are just assuming that the error term is normally distributed, not that the variables are. But good news, even past that, it doesn't actually matter that much if your errors are normally distributed. If your errors are not normally distributed, the thing that makes that it doesn't work is that it makes it so that we can no longer prove that our ordinary least squares coefficient is normally distributed. It might follow some other distribution that's not a normal distribution. But it's usually pretty close to a normal distribution anyway, unless your errors are really, really weird, in which case you probably got other problems besides just normal errors. So that's one we can sort of brush to the side. All right, next, we are also assuming that our error term is independent and identically distributed, which might be a term that you've heard before in statistics applications. So let's take each of those one at a time and think about some cases where that might not be true. So first of all, what is it? Independent and identically distributed means that each individual error term, so your error term, my error term, this person's error term, that person's error term, each of them follows the same distribution. They are identically distributed. And they are uncorrelated with each other. They are independent. So knowing my error term does not tell you anything about that person's error term. All right? So what are some ways in which we might have error terms that are not independent and identically distributed? Well, one way that we can have error terms that are not identically distributed is in the case of heteroskedasticity. Heteroskedasticity is what happens when the variance of the error term is related to our predictors, x. So we already made the assumption that our x is unrelated to the error term itself, but that doesn't necessarily mean that the variance won't still be related to x. Here's an example of a graph where we have some heteroskedasticity. Now, I want to be clear, not all data with heteroskedasticity looks exactly like this graph. This is just one example of what's called a fan version of heteroskedasticity. Other shapes could be there too. But you can see here what's happening, right? If you sort of look at the amount of spread that you have around that line, on the left, there's very little spread. The variance of the residuals, and thus probably the variance of the error terms, is small for low values of x. But as we move along the line to high values of x, things spread out. The variance of the residuals gets bigger, and thus probably the variance of the error term is also getting bigger at the same time. So that is one way in which we can have error terms that are not identically distributed. How about some error terms that are not independently distributed? How is it possible that error terms could be correlated with each other? Well, two common ways in which this could occur. One is autocorrelation. Let's say that we have data that we've measured over time. Either we have time series data where we are measuring a single value or a single observation and how it changes over time, or perhaps we have panel data where we have many different individuals and we're measuring all of them repeatedly over time. Well, in all those cases, you might expect that the observations are going to be correlated to their closest periods in time. So let's take this graph of unemployment rate, for example. I fit an ordinary least squares line onto it, and you can already tell that that line doesn't look very good, right? There's clearly something going on that we are not mapping. And you could say, oh, well, there's the shape that we have not accounted for, but there's also autocorrelation. If I pick a particular point on that graph, I can tell you that the points just on either side of it are likely to be closer to it than they are to other observations in the data. There is autocorrelation. If I happen to be above the line this period, I'm likely to be above it next period too. And since being above the line is our residual, right, how far above the line we are is the residual, and thus our representation of the error term, we hope, then we think that our error terms are likely to be correlated with each other across time. This is autocorrelation. And it's likely to pop up really anytime you have a measure that is repeatedly measured. Another way in which we could have error terms that are correlated with each other is clustering. Let's say that you have data that is collected in a hierarchical manner. Let's say you're doing data on some sort of test in schools, right? You have all the students take a test. Well, students who are in the same school are probably going to be likely to have similar test scores, or at least more similar to each other than they are to students at a different school. And even within that school, students in the same classroom who maybe share a teacher are likely to have more similar test scores than they are to students in other classrooms, right? And so inside of the different groups, you might expect the values to be clustered together. And then once you add in a model that you're predicting with, and you look at the residuals, you might also expect that the residuals, and thus the errors, are also likely to be clustered together. That this classroom's error terms are likely to be closer to each other than they are to a different classroom's error terms. The error terms are clustered within classroom. And when this happens, obviously the error terms are correlated with each other. If I learn about your error term, then that tells me some information about the error terms of people in your class. All right, so those are some ways in which our error terms could be things that would not accord well with the calculation that we already did. And I'll tell you why it might mess those things up. In particular, if we look back at the equation that we have for the standard error, that's the sigma squared that we have in the top, that is a measure of sort of our prediction error. It's a measure of our variance of our error terms. But we're not going to do a very good job measuring the variance of the error terms if we don't account for the heteroskedasticity or the clustering or the autocorrelation. If we simply look at the variance of the error terms overall, ignoring all of those relationships, we're going to be ignorant about how the sampling variation is going to affect things. We also might see some weirdness in the variance of x as well. So we need to adjust our calculation to be aware of the presence of these failures of assumptions of our error terms. Now, there are many ways to do this. A common approach is what's called a sandwich estimator. And what sandwich estimator does is it does this exact same calculation that we have right here, except it just calculates sigma squared in a slightly different way that accounts for the presence of different kinds of problems. And it changes the calculation of the variance of x in slightly different ways that allow for the presence of these problems. So there are sandwich estimators for all three of the problems that I mentioned: heteroskedasticity, autocorrelation, and clustering. They are, unsurprisingly, called heteroskedasticity robust standard errors, heteroskedasticity and autocorrelation robust standard errors, or heteroskedasticity and autocorrelation consistent standard errors, and clustering robust standard errors. That's what they do. They don't do anything particularly wild. They just take this same calculation that we already have, but they calculate the sigma squared and the variance of x in slightly different ways that say, hey, I'm going to allow for the fact that there is heteroskedasticity, autocorrelation, or clustering, and adjust my calculation to account for that. The actual process of doing those calculations I'm not going to go into in this video, but you can look in the book or even on Wikipedia to see exactly how it is done. But to give one example to sort of give you an idea of what it's doing, the heteroskedasticity robust sandwich standard error is going to say something like this. Okay, well, let's look back at that graph. We can see that for low values of x, we have low amounts of variation, variance in the error term. For high values of x, we have high amounts of variance in the error term. And when it calculates the standard error, it will say, hey, I see all those high x values. I'm going to sort of inflate the presence that you have in my calculation of the variance of the error terms because I know there's a lot of variance over there. And these ones down here, I'm going to shrink your influence on my calculation. And by doing so, it gives you an estimate of the variance of the error terms that is more properly what you would actually get in sampling variation when you have a graph that looks like this. So those are some things that can go wrong with your error terms and things that will affect your calculation of the standard error. Conveniently, there are ways to recalculate the standard error that allows for these problems to be there, but you can still get a proper calculation of what your standard deviation for your sampling distribution looks like. You just have to make sure that it knows that you're going to allow for the presence of these things. Which is probably a good idea. A lot of economists would pretty much always use heteroskedasticity robust standard errors, just assuming that it's always going to be a problem, which I don't know if that's necessarily a wrong thing to do. That seems okay to me. All right, that is it for this video. Thank you.